Hi everybody, so we're going to do one of my favorite lessons in this whole unit, and really of almost any situation, and that is the greenhouse effect. Okay, so the greenhouse effect, the big goal of this is to look at the incoming radiation from the sun, use the physics that we learned about the radiation of black bodies, not only for the sun, but for the Earth. The Earth is going to play the critical role here, and look at how we can use those to model what the equilibrium temperature of the Earth should be based on the incoming radiation of the sun, and then make an adjustment for the greenhouse effect due to greenhouse gases. So we're going to do this in stages. Excuse me. And this graph you see in front of you, put out, I don't know, 10, 15 years ago, and it's probably been updated since, but it's fairly accurate. This Earth's radiation budget. There's a lot going on here, but it's a really, really good representation of incoming radiation versus outgoing radiation. And the most important big idea of this whole lesson is that an object, in this case the Earth and its atmosphere, or at least the lower part of its atmosphere, called the troposphere, reaches equilibrium when the input equals the output. Whenever there's a difference between the two, the Earth is going to either warm or cool. And most people don't realize that. They just think that the temperature of a body is just what it is, without giving thought as to what's going in. And they often don't even realize there's always an outflow of radiation by virtue of just having temperature. So we want to keep that in mind as we go into the details. Okay, so I will quantify this in a bit in the notes below, but the incoming thing is, the most important number to start with is this incoming solar radiation of 342 watts per square meter. Okay, and so what I want to do is kind of keep track of our pluses and minuses, if you will, in this little ledger. Now you might be thinking, wait a second, didn't we learn that the solar constant, IS, was around 1440 watts per square meter? And it is, but that's from the sphere of the sun. And so when we got to look at what if we, and I'm not going to go into a lot of detail here, and I don't want you to get sucked up in this, but when we average that over the entire surface of the Earth, take into account that certain parts of the Earth get more direct radiation than others, and the fact that the Earth rotates, what we can average over the entire Earth is 1/4 of this value. So if I take 1/4 of 1440, I get roughly what is on that graph, and I'm going to stick with the 342 watts per square meter that's given on that graph. So I just want you to understand where that comes from. It's essentially 1/4 of the solar radiation. Okay, now, as we said also in the previous tutorial, even though the upper atmosphere is getting an intensity of that, okay, not all of that reaches the ground or the lower atmosphere. So we got to subtract out any radiation that's being reflected back into space. And we can see from the graph that essentially happens at two places. It happens essentially here because of clouds, aerosols, and atmospheric gases, and then we have it happening here because of the surface, especially icy surface, etc. So that is a measurement that we talked about before called albedo. Okay, so number two, in terms of the influx, so looking at what's coming into the Earth. So this is obviously the most important. Without that, nothing else really matters. So we have reflected radiation. Okay, and we mentioned before this is measured as something called albedo. So the equation for albedo is given a symbol alpha, is simply equal to your output, reflected, if you will, intensity, divided by your input. It's simply a ratio. Okay, and we want to understand, qualitatively at least, what factors increase or decrease albedo. And again, we talked about this with the PowerPoint. Okay, so key things you want to understand: cloud cover. Okay, and cloud cover is hard to measure, super hard, because clouds aren't covering big chunks of the Earth at any one time, and they don't last for decades or whatever. They last on the order of hours. Easier to measure are aerosols. Okay, And those aerosols are little fine particulates that we emit in the atmosphere, excuse me, due to pollution. Volcanoes can be a huge source when there's a major eruption. Okay? There is certainly latitude affects albedo. In other words, latitude goes indirectly to how much ice or snow. We expect more ice or snow in terms of sheets and glaciers in the low latitudes, and we don't really expect to see any in the high latitudes. I got that backwards. The low latitudes are the equator. The high latitudes are the poles. That's where you're going to see a lot of albedo. So these are the three major factors that will increase albedo. You can also decrease it by water and vegetation, water and land. So open water is a very good absorber, and vegetation, well, it's vegetation because it wants to absorb light. So when we put it all together, the albedo of the Earth is about 0.31. Of course, it fluctuates, especially with clouds, but the clouds aren't a huge contributor, so they're not going to increase it or change it that much. Okay, so if we take 0.31 of our input, then we see what is reaching the surface, or excuse me, if we subtract out 107, right, we multiply that, we see the net reaching the ground is a very important number, 235 watts per square meter. Okay, so that's what reaches the lower atmosphere and the ground. That's what's being absorbed on average. So that's what we're absorbing day after day after day after day. So the natural question is, if we're continually absorbing that, why isn't the Earth just heating up and heating up and heating up and burning to a crisp? Why is the Earth's average temperature around 68, 70 Fahrenheit or 20 degrees Celsius? And it's the same reason that if you go in your home, if you warm up an oven, well, you got to be careful about that. So let's say I have a burner on in my stove, or a flame, and I put a pan on it. The pan will warm up, and it'll keep warming up, and keep warming up, and in theory, it can only get as hot as the flame. However, it will never get there, because while it's warming up, it's going to also give away a lot of its energy, especially in the form of radiation. So the Earth does the same thing. As it warms up, it gets rid of a lot of radiation as an outflux, so we will eventually reach a equilibrium temperature when that outflux equals the influx. Influx, based on the other model, is more or less constant. Okay, so that's a simple point, but it's a point that a lot of people completely overlook. Okay, so as a warm, it radiates energy at a wavelength, and it's generally in the infrared, corresponding to its black body temperature. Okay, so we want to make sure we understand cause and effect. If you were to look at the Earth with a satellite, let's say from afar, and you had a spectrometer that could see many wavelengths, you would see the Earth does not glow in visible light. Yeah, it might reflect some visible light, and you can see it with the naked eye. But if you look at the radiation coming from the Earth, it's all in the infrared range. And it's in the infrared range because of the Earth's average temperature as a black body. So we want to understand then is what that temperature is, thus giving rise to the infrared radiation, because it's infrared radiation that's crucial to the greenhouse effect. Okay, so our overall idea is that intensity that's coming in has to equal intensity out when thermal equilibrium is reached. So now we're going to apply the equations that we've learned and then some of the numbers that have come up so far. Okay, so ultimately our intensity in equation is the solar constant times 1 minus alpha. So that's building in, that doesn't look like much of an alpha, the albedo. Now when I put that IS there, I don't mean the 1440, I mean the average value for this over the whole surface of the Earth. So I don't want you to be confused by that. And then the outgoing intensity. So like we said, the Earth has temperature, it has to radiate away energy. And we learned that equation in a previous tutorial. That's Stefan Boltzmann's law. So that's going to be equal to epsilon, sigma, and then t to the fourth. Now note I don't put the area in there because the equation for Stefan Boltzmann was power has the area in there, and if intensity is power divided by area, then the area part up here cancels out with that, leaving us with this. okay? So if you're not confident with that, go back to the equations or ask in class. So if we know at the thermal equilibrium, intensity in equals intensity out, what I can say is then, I'm going to solve here, I'm going to just put in for the intensity in, I'm going to put the 235 that we established on the front page. And then I'm simply going to set that equal to epsilon sigma t to the fourth. And we can now solve for the t. We know sigma is 5.67 times 10 to the negative eighth. What are we going to assume about epsilon? Well, let's take the simplest case. The Earth is a perfect black body. Okay, and so this is 5.67 times 10 to the negative eighth units, and that's 235. So if I solve for t, and you can work that out for yourself, we get t equals 253. That will come out, and that's not Celsius, that's Kelvin. Okay, and therefore our equilibrium temperature, I'm sorry, this should have been inside the box, I got moved over. If we go to Celsius, is negative 20 degrees Celsius. Okay? Wait a second though. The Earth's average temperature is about 20 degrees Celsius. So we clearly have something wrong. I'm sorry, that's not 20 degrees Celsius. My bad. It's a little too warm. It's 15 degrees Celsius. Okay, so there's a huge mismatch here. But before we worry about that mismatch, again, make sure you understand this idea here. Input equals output. The input is based on the sun and the albedo. The output is based on the warmth, the temperature of the Earth. And so when there's initially, if we turn the sun on, the input is going to be everything. There's going to be no output. But as we absorb the energy, we warm up. And so our output grows, but it's going to be less than our input. And it keeps growing and growing by the fourth power temperature until it equals the input, assuming the input is staying constant. Okay, so we'll have a spreadsheet that allows us to figure that out. All right, so get back to the problem. If this simple model predicts a frozen Earth, yet we know our Earth is much warmer, what's wrong? Okay, and so what are we ignoring? Well, the answer is the Earth's emissivity is not 1. Okay, in other words, the Earth is not a perfect black body. And there are many reasons for this, but the very, very important one is that greenhouse gases, GHGs, do not let all of the infrared escape. Okay, so in other words, if I apply this temperature to Wien's law, we will see that the radiation coming from the Earth is in the infrared band. Okay, and that will hold for a lot of temperatures, even for this temperature, which would be closer to around 300 degrees Kelvin. So if the Earth is radiating infrared because of this rough range of temperature, certain gases we know vibrate with the overlap vibration with the frequency, and so it'll be absorbed. And then if it's absorbed, it just doesn't sit there in the molecules. The molecules jiggle faster, and what they'll eventually do is re-radiate it in all directions. Some of it up, some of it sideways, but importantly, some back towards the Earth and the lower atmosphere, and it causes the net influx to rise, and I'm not going to go into the details of this, to 390 watts per square meter instead of the 235. Okay, so if we go back to the first page, this one, here is this surface re-radiation because of this greenhouse effect. So I'll let you work out the numbers from here, where that 390 comes from. And it's not critical you do that. But that's really the net result of the greenhouse effect, is that we absorb more than we normally would because of that re-radiated infrared, because of the blanket effect of the greenhouse gases. Another way we can look at that, an alternative way, is that the influx isn't affected, but the outflux is reduced. It's retarded, if you will, because of the greenhouse gases, so that instead of upping the influx to 390, I could insert for emissivity a number. I think it would be close to like a 0.68 or something like that. That would express our influx. Okay, so I'm going to stop here. Next video, we're going to solve then, applying the greenhouse effect, what the new equilibrium temperature should be.